All right, welcome to our next set of notes. I have a question for you. How do you catch a unique rabbit? Unique up on it. Well, how do you catch a tame rabbit? Tame way. Unique up on it. All right, we'll go ahead and get started with our notes today. So today we are talking about exponential growth and decay. We're going to start on the front side of our notes talking about the exponential growth. So what I have is just a quick definition. This occurs when a quantity increases by the same rate over time. And then I have my formula right here for you. A is your original amount. R is your rate. Okay, real quick, rate will be written as a decimal. You could do a fraction, but you'll see that as a decimal is much easier. And this rate has to be a value greater than 1 when we are talking about a growth, an increase. Okay, so let's go ahead and write in that for growth, this will be greater than 1. And then T represents time. So again, we have A, the original amount. And what I want you to kind of make note of is we have worked with geometric sequences and exponential functions. And notice the very first value that we put into our equations have been an initial amount, an initial value, the first term, and now the original amount. So it does all correlate, okay? And then we have the exponent, and then in this case we have it to time, and then within parentheses it's going to be some sort of growth factor, okay? Or common ratio. The first example, let's go ahead and read through and solve this. We have the original value of an investment is $1,400, and the value increases by 9% each year. So I'm going to make sure I underline it increases 9% each year. We're going to write an exponential growth function to model this situation. Then find the value of the investment after 25 years. So this is similar to when we were working with geometric sequences, the explicit formula where we had to write the rule and then solve for a specific term. Right here, it says we are going to write the exponential growth function. So that is our first step, and then we'll find the value. So let's go ahead and get started with our formula where we have y equals, our original amount is going to be this 1,400. And then using the rest of our formula, 1 plus, and then our rate. Our rate is an increase, 9% each year. We wrote down, we write it as a decimal. So let's convert 9% to a decimal. That's going to be decimal point 0.09. And our time, okay, in this case, it'll be 25 years. Okay, so we'll have it to the 25th power. Okay, sometimes they'll say unknown years, and then you would just leave it as the variable t, some sort of variable. Oh, you know what? I boxed this in just a tad too early. What I do want us to do is take one step of simplifying within parentheses. Sorry. So I'll make sure to do that on the next problem. So it's going to be 1,400 parentheses. We'll go ahead and add this together. And now to the 25th power, and there you have it. Okay. Now it says find that value. So again, this was my function. We'll go ahead and find that value. And so again, we're going to just go ahead and use our calculator. So either a graphing calculator, some sort of scientific calculator like this one. Again, order of operations, we want to do what's inside parentheses first. To the 25th power. So it's the same kind of button on the graphing calculator. We hit enter, and then we multiply that by 1,400 to get our value. Now we are going to have to round. We're going to round according to the story problem. In this one, they are wanting to know a value in dollar amount. So we'll round to the nearest cent. So this we have 12,000 $72.31. So that's my second answer for this one. And you know what I'm going to do is, just to avoid any confusion, we'll do number 2 next time I see you in class, okay? So that way, to make sure that you get this down. But let's go ahead and do number 3 together right now. So number 3, I have the function y equals 14,999 times the quantity 1 600ths to the power of t. It represents the annual sales y for a company t years after 2010. By what percent does the annual sales increase each year? Okay, so they want to know the percentage of increase. If we use our formula, so let me scoot this paper down a little bit. Rate is how much we change by, and so that's what we have to solve for. Okay, so if they give us 1 600ths, we're going to break this apart to this formula. 1 is just a part of the formula. Okay, and then we have 600ths. And so it's this 600ths that we would have to convert to when it says by what percent. So it is 6%. Okay. And that's it for part A. Part B says, what will the sales be in 2017? Okay, so this function starts after the year 2010. So we can do 2017 minus 2010. You don't have to show this work. You can know that it's going to be 7 years for your time. We would just, this is the work that you need to make sure you're doing, is write down 14,999 times the quantity 1 600ths to the power of 7, because it's 7 years. Again, in our calculators with scientific notation, or scientific calculator, 1.06 to the power of 7. We hit enter. We're going to multiply that by 14,999. And again, they are talking about sales, so this is a money problem. We'll go ahead and round this to the nearest cent. Looks like we have 225,543 and 4. Oh, did I do this one right? My answer key is different than what I have right here, so I was just copying from the answer key. So looks like it's 22,000. Sorry about the typos. Again, it looks like maybe the answer key is wrong, and hopefully I didn't make a mistake before. And 95 cents. There we go. And if there is a mistake, I'll let you guys know next time I see you in class. Okay, hopefully this is enough. So we'll do 4, 5, and 6 next time I see you in class, okay? Let's go ahead and flip this over to exponential decay. Okay, so exponential decay, this occurs when a quantity decreases by the same rate over time. Okay, we have our formula. A is going to be the same thing, where it is an original amount. R is my rate. We'll be writing rate, converting it to a decimal. This time, since we are talking about a decay, this value, this rate, will be less than 1. And t is our time. Okay, so let's go ahead and try this and kind of see what these problems are like. So for problem number 1, an investment of $8,200 loses value at a rate of 2% per year. Write an exponential decay function to find the value of the investment after 9 years. So our first step is going to be to write that function. Okay, so write that decay function. So I'm going to use this formula right up top. I have y equals the original amount is 8,200. Okay, it's telling me it's losing value, so I know it's a decay, so it's going to be 1 minus my rate. My rate is 2%, okay, and it is after 9 years. And so all I'm going to do is simplify what I have inside parentheses. Okay, and that's it. That is the function that we'll go with. Okay, 8,200 times the quantity. Oh, I added and did not subtract. I'm doing these notes like I didn't have coffee yet today, but I did have some. Maybe not enough. Okay, let's go ahead and try number 2. So we'll try number 2 right now. So for number 2, a farmer buys a tractor for $50,000. If the tractor depreciates 10% per year, write an exponential decay function to find the tractor in 7 years. As I read this problem, I realized I did not finish number 1. I am really off today. So let's go ahead and actually solve number 1. So for number 1, again, use the scientific calculator. Then we'll go back and finish number 2. And I think what I'm going to do is shorten these notes than I originally thought, just because I'm making typos left and right. So we have to do exponents first. Order of operations, we'll multiply that by 8,200. And so, at least this time, my answer does match the answer key. There we go. Number 2, I said we were going to do this one. So again, we have our original amount of $50,000. It's depreciating, so I know it's a decay, and it's depreciating by 10% per year. We're going to write that function after 7 years. So let's go ahead and get started with y equals the original amount. We underline that as 50,000. It's going to be 1 minus. It's minus because it's depreciating. It's a decay. 10% as a decimal. Here we go, 0.10 to the power of 7. And so we'll go ahead and simplify what we have inside parentheses. So we have 50,000, 0.90 to the 7th power. Okay, there we go, doing better with that so far. And then again, let's go ahead and use our calculator, doing exponents first. Multiply that by 50,000. And so let's go ahead and write this value down. We have 23,914.85 cents. Okay. And then we'll just do number 3. For number 3, the function p equals 28,000 times the quantity of 0.975 to the power of 15. It represents the population p of the town of Haywardsville after t years. By what percent does the population decrease each year? So we know it's a decrease because it's less than 1, but they're pointing out again that it is a decrease. And so what we're working with, if we think back to the original formula, okay, to figure out that percent of decrease, we're going to use that to help us. So it is going to be 0.975 is equal to 1 minus, and then we have to think about how 1 minus what gives us 0.975. This is going to be 25 hundredths. Okay. Oh, I forgot a 0. And so really, what I should be doing is I could do 1 minus 0.975 to get my final answer of 0.025. And then I rewrite this as a percent, so I move that decimal point 2 places to the right to get 2.5%. Okay, I'm going to call a day on these notes. I apologize for all my typos and mix-ups, so hopefully it'll be better next time and in class better as well. All right, I'll see you guys next time.